So in this video, I'm going to be solving this problem here. And in this part, we're going to be deriving differential equations to solve the fluid levels in these three tanks. So to start this problem, I'm going to make a diagram of the situation. So to start off, we have our three tanks. So there's the first tank, second tank, and third tank. And then it says that they are interconnected at the bottom. And this one will be going out. And then there also is flow going into the second tank. And also all of them have different fluid height levels. And each of them have different cross-sectional areas as well. So now I can label these as well. So this will be height 1, height 2, and height 3, and then area 1, area 2, and area 3. This will be our Qn, this will be Q1 and 2, and Q2, 3, and then also our Q out. Now it also gives us our Q in as well, and it says that that is equal to proportionality constant Kc multiplied by the difference between the fluid level set point for the third tank and its actual fluid level. So we're going to call that height set point for 3 minus the actual height of 3. So now our goal is to get Q12, Q23, and Q out. So in the problem here, it does state that the magnitude of the flow between the tanks is proportional to the square root of the difference in fluid heights between pairs of tanks. So for Q12, that will equal the proportionality constant, which is going to be alpha for each of these. So I'm just going to label that here. Alpha 1, 2, alpha 2, 3, and alpha out. So it's going to be equal to the proportionality constant times what it says here, the difference in fluid heights between the pairs of tanks and the square root of that. So it'll be our height 1 minus height 2 all to the 1/2 power. But we do not know which of these heights will be greater. Obviously in my drawing I have this one higher, but we don't really know which one will be greater. So if it would happen to be that height 1 is greater than height 2, then our square root will work. But if height 2 is larger, then we get a negative number here, and we can't take the square root. So to fix that, we are going to make this an absolute value. So this will be the absolute value of h1 minus h2. But now since we have done that, then our flow, we won't know if it'll be going in the positive direction or the negative direction. So to figure out that, we're going to just get the sine of our h1 minus h2. I'm just going to make a little bit more space here. h2, h1 minus h2. So now if we will get a positive number, then we'll know that we'll have the positive flow, and then if it's negative, then we'll know that we'll have negative flow going from the higher height to the lower height. Or if the higher height's here, to the lower height here. So Q23 is going to be very similar to this, but instead of between 1 and 2, it's going to be all this between 2 and 3. Which is going to be the sine height 2 minus height 3, and then this proportionality constant 2, 3, height 2 minus height 3, all to 1/2. And then finally for our Q out, it's going to be fairly similar, but obviously we're not going into another tank, so it's only going to be this one tank, and it'll also always be positive, because we'll be always going that way. So for this one, all we're going to have is our proportionality constant, which I'm also just going to call this 3. So we're just going to have our proportionality constant, and then times our height 3 square root, like that. Let me write this out a little bit nicer. Height 3 square root. So now we are going to want to get equations for each of the heights. So we know that the heights are going to be changing over time, and also the volumes are going to be changing over time. So we can figure out that the change in volume will equal, and since volume equals the cross-sectional area times the height, change in volume will equal the change in area times the height. But for each of our containers, the area is going to be staying the same. So we can take that out, so our change in volume will just equal area times the change in height. So now comes the material balance part of this problem. So that means whatever's coming in is going to equal what's coming out. So I'm going to make an equation for each of the tanks. So starting with tank 1. Tank 1. So it'll be our area 1 times dH over dt. This will be our height 1 is going to be equal to, and since there's nothing coming in here, it's just this Q12 that's coming out, so it'll be equal to our negative Q12. And then for tank 2, will be our area 2 times dH2 over dt will be equal to, so Qn and Q12, so Qn plus Q12, and then minus our Q23. Q23. And then finally, tank 3. Tank 3 will be area 3 times dH3 over dt will be equal to, and now it's our Q23, and then minus our Q out. And I'm also just going to rearrange these to make it dH1 over dt equals negative Q12 over A1, and then dH2 over dt will equal Qn plus Q12 minus Q23 all over A2, and finally dH3 over dt will equal Q23 minus Q out over A3. So those are our derived differential equations that is going to help us solve for fluid levels in the 3 tanks.